Good morning. Welcome to Finding Our Path, how we're trying to improve Active Directory security in South Seas ABE with Andy Robbins, Will Schroeder, and Rohan Vazarkar. Before we begin, a few brief notes. Stop by the Business Hall located in Mandalay, Oceanside, and Shoreline ballrooms on level 2. The Black Hat Arsenal is in the Business Hall on level 2. Lunch will be in Bayside AB from 1 to 2:30. And don't forget the merchandise store on level 2 and the session recordings from Source of Knowledge. They have a desk on every level. Before we begin, please put your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick it up. All right, let's give a round of applause to our speakers.
There's a clicker.
Ready?
Yeah.
All right. Hope everyone's doing awesome today. We're going to be talking about the greatest tool of all time, Bloodhound.
Power view.
Yeah, Power View, actually. All right, so our talk is called Finding Our Path, how we're trying to improve Active Directory security. This is us. I'm Rohan.
I'm Will. I'm Andy.
All right, introduction's done. All right, so first of all, we're going to talk about a little bit of background here. We released the Bloodhound project about 3 years ago now, and we had some very significant problems to solve when we did so. I do want to acknowledge some prior work. These are really, really cool things, especially like Metcalf's blog here. And check all these out. Here is where we kind of started when we were trying to build Bloodhound. So we're standing on the shoulder of giants here. Wouldn't have been possible without that. All right, what is Bloodhound? Bloodhound is the tool we wrote, and our goal was to apply graph theory to Active Directory. We wanted to simplify privilege analysis in Active Directory, which if anyone has tried to use built-in tools in Windows knows that is not easy. It's very, very arcane and not very easy to navigate. So we wanted to visualize relationships in Active Directory and essentially build what we call Google Maps for Active Directory. So we had a bunch of problems we had to solve. One of them was, how do you go from one place in Active Directory to another? Our background is pen testers and red teamers, and often we'd drop it in a network, and we were given an objective: go get healthcare data, go get DA, whatever it happened to be. And our original process would take a really long time, so this was kind of our solution to the problem. Other problem we wanted to solve is, how do you escalate your privileges without scanning the network many, many, many times? I'm going to demonstrate what I'm talking about in like the next slide here, but we hit the network a lot when we used to operate. And also, how do you analyze permissions more efficiently than built-in tools? So we're going to tell the tale of two APIs. The two APIs that Microsoft graciously provided to make our lives much easier, but also was the basis for everything we're talking about here. The first one is net session enum. Now, the built-in Windows net command has lots of juicy stuff in it, and one of them is net sessions. And underneath, net sessions just uses the net session enum API call. What's fun is that the actual API call has a nice little field for the server name. So because the API call is a little bit more complex than what the net session binary does, by implementing it directly, we could enumerate remote server sessions. So now we have a way to tell who's logged in where. The second one is net local group get members. Lets you retrieve a list of members of a local group. The one which we were almost always most interested in being the administrators group. Administrators are awesome. It lets you do whatever you want on a system, get rid of all those pesky EDR solutions. So again, this one has a server name parameter. So this allows us to enumerate remotely and check who's a local admin on remote computers. So let's tell a little story here. We have a pen tester named Nat Melson, and he is pen testing the cornhub.io domain. This is a nice little tiny office in Indiana. Got to make sure that they're really secure. So they have about 9 computers. Nat Melson fishes and gets initial access on the computer in the middle right there. So this is our old methodology here. First thing you do, you run find local admin access in Power View. And now you've hit every single machine once. We're going to put a little number underneath each machine here so you guys can keep track. We found out we have admin on the 2 machines that have flags on them now. So next thing we do is we run net session enum on those. We try to see who's logged into those machines so we can get some kind of idea of what kind of creds we might get. So we look at the usernames that come back and we find absolutely nothing of value. They're not domain admins. They're not in any like super privileged group. So let's just like blindly pick one computer here. We're gonna go to the computer number 4. All right, so now we're over here. What's the next thing we do? Hey, we hit the whole network all over again. We're gonna do find local admin access one more time because now we have a new credential that we've taken from this computer and we wanna know where we have admin. So now we found admin in a few more places. And again, the number increments. Now we have to get net sessions on those computers. So now we're up to 3 on those. And we decide, all right, let's go to the bottom computer over there. And this one looks juicy. I think it's a DA. And we go over there. Sure enough, we're domain admin. Yay, we won. But at this point, we've hit every computer at least twice, some 3. And this is a very, very, very small network. This is just 9 computers. As the network scales up, this number just keeps increasing. And as each step increases, there's more and more network enumeration that's being done. That's not good. It's very, very, very slow to do this process. When we used to run this process in larger environments, this would take us weeks or months to execute. And weeks spent doing privilege escalation is a lot of time that removes post-exploitation from your assessments. As you get more and more network hits, your chance of getting caught also increases. And if you're on a red team, getting caught is no bueno. And as you get bigger and bigger networks, keeping track of what you're enumerating gets harder and harder. We used to try and solve this by using like Excel pivot tables, which is like the worst thing you can possibly touch. So we wanted to do it better. And as it just so happens, an entire branch of math that we all fell asleep during math class for exists to solve this problem. So why are we doing this ourselves? So let's do it the new way. So we drop in on the network right in the middle here, and we run data collection for Bloodhound. We hit every computer in the domain twice, once for net session, once for local admin. But instead of just blindly picking something, we feed all this data into our tool, and then we say, let's make educated decisions where we need to go. So instead of having to go to one computer and do enumeration again, we know exactly where we need to go and what we need to hit in order to get to where we need to be. So there you go. You do 2 steps, you get to DA. No more network enumeration, no more extra steps. You're just happy now.
Sure.
All right, we're gonna swap out our cable here. But wait, there's more. When you run SharpHound, you're not just getting basic local admins or sessions. You're also getting lots of other things like, are there any Kerberos misconfigurations? Who belongs to what group? And how is that unrolled? Are there any abusable ACLs in the environment that you could use, which might even prevent you from needing to move laterally to another computer? Is there MS SQL servers that you might have admin to because of service principles? And if you do, can you use those to get where you need to go? So in the real world, we actually created Bloodhound because we were in a massive, massive organization with thousands of endpoints, hundreds of thousands of endpoints, as it were. Getting domain admin in a single domain in this network took weeks. Now, the organization had literally hundreds of domains. This definitely did not spark joy, knowing that getting to the top of the root was going to take months, potentially. We built Bloodhound as a proof of concept, and we ran it. Data collection took, I don't know,
48 hours.
About 48 hours. And it showed us a path that went through 7 different domains to compromise the forest root. So 48 hours to go from beginning to end versus 1 week to get just DA in one single domain.
So it's kind of the history of Bloodhound, the genesis, how it came about. We've been doing some new work in the past year or so, adding some new attack edges, adding some cool new features. So we wanted to go through an example attack path and show some of the more kind of niche, cool, like new Kerberos abuses that we've been able to implement in. So as we're going through this attack path, think to yourself, Okay, these misconfigurations have been in the network or might be in your network for years. Would you have had any way to actually analyze and execute these things or actually realize the implication and the risk that some of these components would have? But first, we're going to talk about Kerberos. There's an element in Kerberos called resource-based constrained delegation, where the general motivation for delegation in general in Active Directory is a way to impersonate users, just do user impersonation from the Active Directory context. Resource-based constrained delegation, as opposed to unconstrained or classic constrained, is a modern, so server 2012 plus, way to safely allow this type of user impersonation in the Active Directory context. Why is this needed for delegation in general? So the classic example is if a user is authenticating to a front-end service, say a web server, that web server may need to impersonate that user when they're authenticating to a different back-end service, say a SQL database. So we've had some people say, like, why does Microsoft allow impersonation or delegation at all? And there are legitimate use cases for it. The first take at it that Microsoft did with unconstrained was very dangerous for different reasons. The second take they took at it with constrained had its own kind of elements of potentially domain takeover depending on things. So this is their third take at delegation. And overall, it's a good system, but it has unintended consequences that we love as pen testers. But diving a little bit deeper for resource space, how it actually works, I'm not going to spend 10 minutes going over all the Kerberos internals and all that. But resource-based constrained delegation is implemented as a security descriptor, a discretionary access control list, on a target resource or computer object. So this DACL is stored as a series of binary bytes, and the MSDS allowed to act on behalf of other identity, it's a bit of a mouthful, property. This is just a simple ACL that defines who is allowed to impersonate any user to that target system. The impersonation itself is executed through a series of two Kerberos extensions called S3U2 self and S3U2 proxy. Why does this matter? So we had known about this for a while, and one of the things we really cared about when we started Bloodhound and doing the ACL-based ingestion components is we wanted a computer ACL-based takeover attack primitive. What do we mean by that? So for a user ACL-based primitive, we could, if we had generic all or kind of edit rights, admin rights over a user object itself, we could reset their password. That doesn't work with computers because they'll become disjoined from the domain. So we've been waiting for an ACL-based primitive for this. And in the spring of this year, Elad Shamir released his really, really awesome wagging the dog post on resource-based constrained delegation abuse. And his big finding is that non-portable S3U2 self tickets will still work for S4U2 proxy, specifically in the case of resource-based constrained delegation. So what does that mean if you're not versed in Kerberos? Is this grants us a generalized ACL-based computer takeover primitive. What does that mean in English? If we can modify this one particular property on a target computer object, we can completely compromise that computer and take it over. We're going to show this in an attack path. So first, Andy is going to show what this attack path would look like in Bloodhound.
So here's the Bloodhound interface. Whoa. Here's the Bloodhound interface, and we're saying the domain object in the contoso.local domain, give me the shortest attack paths to there. And the graph will find all the shortest paths that exist from any node in the domain to that object. This attack path starts at this desktop 001 computer. It has a session for Bob accounting. That user belongs to this group called accounting support. Accounting support belongs to accounting admins. So through security group delegation, accounting admins has admin rights to accounting 001, and so does Bob. This computer in accounting has generic right over an exchange system, which belongs to the exchange trusted subsystem group in AD.
Our favorite AD group.
Favorite AD group. That group has tons and tons of privileges, including write DACL on the domain head. So we're going to execute this attack path in these video demos. We're going to skip part one just because it's a very basic thing. It's local admin on a computer, so psexec, WMI, whatever you want.
So we're assuming that we're going to be on this accounting box. We compromised that first hop. We're going to show the verification of the ACLs that Bloodhound was able to find. But first, we're on the system, we're on accounting. We're going to escalate to the system user context. But showing like, okay, even whatever context we're in, we do not have, we do not have rights over that target box. So we will escalate up to system because the system user context will use the machine account from whatever box you're on. See, access is denied because we haven't actually executed this resource-based constrained delegation attack path yet. So we're going to load up PowerView to do our Active Directory analysis. We're also going to load up Kevin Robertson's PowerMad, which abuses the machine account quota component of Active Directory to provision new machine accounts in a way that we can control. So our target computer in this example is going to be the Exchange server. This is the machine that our current machine has edit rights over. We're going to pull our actual attacker SID. So this is the SID of the computer we're currently on. This is who has edit rights over that target system. Then we're going to show the ACL base. We're just going to pull the DACL, the ACLs, for that target computer on the Exchange box. If we examine the ACE, we see, okay, there's a generic all right over the Exchange system by the security identifier, which happens to match what our current computer security identifier is. So this is just simple verification of the actual ACL information that Bloodhound was able to enumerate. The next steps, we want to actually execute this attack path. We are going to first use PowerMad from Kevin Robertson to provision a new machine account with a password that we control. This is because we need an account, we need complete control of an account that has a service principal name set to actually execute the resource-based constrained delegation path. We're going to grab the computer SID, because this computer SID is going to become the principal in the ACL that we actually construct. The general approach is we need to create this ACL, set it to a particular property on the target, and then we're going to execute the S4U2 self and proxy component for resource-based constrained delegation. So create the ACL, very easy to do in PowerShell. We're going to get the binary bytes to that ACL, and we're going to use that and set against the MSDS allowed to act on, I can never pronounce the whole thing, it's a little too long.
We're allowed to act.
Grab the binary form. We're going to just use a simple LDAP property set against the target. And after that, we're going to pull the ACL to just verify that we actually did the correct LDAP set on this component. So pull the raw bytes. We're going to transform that back into a security descriptor and pull out the discretionary component of the ACL for verification. But still, even after we do this, we're not going to have administrative rights against the target system because we have to go through a fairly complex Kerberos ticket exchange process to actually get the final service ticket that we want against the target. So verification, everything matches up, everything's great. Still don't have admin rights. Okay. The next bit we're going to do is use a tool that we wrote called Rubius, which is a Kerberos abuse toolkit that heavily pulls from Benjamin Delpy's Kikyo project. We're going to hash up our password. Then we're going to use the S4U module, our command in Rubius, to actually execute this whole process, which will first get a TGT for this dummy system account we created. It'll do the S4U2 self to itself to impersonate an administrator, so we're pretending to be the domain admin. Then it'll do the S4U2 proxy protocol transition, ending with a full ticket for CIFS or the file system. We're then going to apply that ticket to our current logon session. And after this, we're able to compromise the Exchange box. Awesome. There we go. All right. It's step one of that whole path that Andy outlined in the Bloodhound analysis component. Step two, we're moving to the Exchange server itself. So now we're on the Exchange box. See, Exchange 001, and this is the computer account that, because of the nesting in Exchange trusted subsystem, is going to have write DACL rights over the domain root. This means that we can grant ourselves DC sync privileges. Again, DC sync is the re-implementation of the DC replication protocol by Vincent Letou and Benjamin. So we're going to run this. And because we have these edit rights, we can't just DC sync immediately. We have control rights over the target. We don't have the DC sync rights itself yet. And you can do any of these like ACL-based modifications. You don't have to use PowerView. Anything that has just LDAP property modification can be used to execute this path. So we're going to use the, let's see, import PowerView. We're going to get we need to get the identity, the SID of the Exchange Trusted Subsystem. We're verifying this, okay. That's 1603. Then we're going to verify some of the ACL information for the attack path. But because of this, we know, okay, Exchange Trusted, we can add and modify an ACL on the root domain object where the principal is the Exchange Trusted Subsystem itself. We're going to grant ourselves DC sync rights. Everything's going to execute through. And now we're going to have, now we can synchronize and retrieve the password credential material for any user in the domain. So say KRB-TGT, we get our hash, we can create all of our awesome golden tickets. So that's a fairly complex path with a lot of moving pieces that even as of like a year or so ago, we would not have been able to enumerate and find. But these are misconfigurations that have existed in domains and existing domains and have been around for years. We just didn't realize the full risk and implication of it.
Okay, so what are we trying to do about this? Do you hear a lot of feedback from my voice?
Yep.
Okay. All right. I'll just keep going. So our answer to this, as far as what can we do to efficiently and empirically understand, enumerate, and remediate these attack paths in Active Directory, is this. It's our adversary resilience methodology. A lot of this is based on this quote from John Lambert in his blog post with this title right here. Attackers think in graphs, defenders think in lists. As long as this is true, attackers win. You would think that we're contractually obligated to have this quote in every talk that we have, but really this is a timeless and extremely insightful quote from John. This is what our methodology looks like. So starting in the top left, we enumerate attack paths, that's using Bloodhound. We analyze the attack paths to understand what patterns we can ferret out from that data. And then the most difficult part of this methodology is in generating and validating those remediation hypotheses. And then finally, we deploy our prioritized fixes and start all over again. We're going to focus here initially on analyzing these attack paths that Bloodhound shows us. So our objective here, we want to find critical low-hanging fruit. We want to generate basic descriptive statistics and measure our overall security posture in Active Directory based on these misconfigurations and user behaviors. So before Bloodhound was created, it was very, very difficult to take any given principal in Active Directory and determine what privileges are held by this principal. Because of the nature of Active Directory permissions, they are discretionary, so they are inbound on objects. And outbound privileges, there is no native way in Windows or Active Directory to enumerate that. With the Bloodhound data, we can. So this is a very basic descriptive statistic that we do for our customers. By the way, everything that we're talking about in this talk is free and open source. So there's nothing in here that is like private or secret or anything. What we're looking at here is just in descending order, what are the most privileged groups in Active Directory? And from this chart, you can see some very immediate insights that would launch you into a little more of an investigative process to figure out why this is the way this is. And one example is the domain admins group. You would expect that to be the most privileged group in AD. In this data set, which is based on real data, the names have been changed to protect the innocent. The domain admins group is barely even in the top 5 of the most privileged AD groups. Sometimes it's not even in the top 10. So Sean Metcalf has a fantastic blog post about how domain admin is, just the tip of the iceberg, and we should be going far beyond domain admin. But still, DA is like the most obvious target. Something else you can look at is there are these help desk tier 1, 2, and 3 groups that you would think they would have a different level of privilege in AD, but for some reason they have all the exact same privilege, which kind of defies our least privilege goals. So in this chart, we can understand what the privileges are that are held by the most sensitive groups, what those most sensitive groups actually are, and start digging into how we can protect the users and other identities that belong to these groups. So what about the other way around? What about computers in my domain sorted in descending order of the most admins that exist on each of those? So this is based on fake data that we created with our Bloodhound DB creator script. And you can see, like, very obviously at the very top, there are these 4 computers that have way more admins than any other system in the network does. In reality, this chart looks exactly like this in real environments, but the numbers are astronomically large. And sometimes that's because the domain users group gets added to the local admins group, but sometimes it's also because a different all-inclusive, non-default, non-built-in AD group has been added either to a privileged group or has been directly added to the local admins group on a system. With traditional auditing tools, you really can't determine this information easily. Bloodhound makes it super easy. So we're going to look at another video. This slide right here, at the very top, we can see that this comp 0003 computer has way more admins than any other computer does. It's part of a group of 4 other computers that have that many admins. So in the Bloodhound UI, we can look up that computer and we can figure out what's going on. Any asset that's tracked in Bloodhound, you can just like Google Maps, you can search for it. We'll click on the computer, and then under this local admin section, we can see that there are 6 principals that are actually added to the domain admins group. But then if we unroll that out, there's actually 500 different users that have admin rights on that system. And it's all because of that right there. The domain users group has been added to the local admins group on that computer. So as far as finding low-hanging fruit in AD, on the assessments that we do, we find this on day 1. And usually eyes are kind of like big and like people are terrified to see this kind of stuff. All right, what about Kerberoast? Kerberoasting fundamentally changed how we operated as red teamers because it gave us a capability to do password cracking attempts on usually very high privileged users in AD from any domain authenticated context and do this kind of offline brute force attack against a Kerb5 TGS ticket. But how do you prioritize as a red teamer what users are actually interesting to go after? So in the Bloodhound data, we can, again, look at any principal and determine what privileges they have. And on red teams, this is exactly what we do. We'll find, okay, here are the 10 users that are Kerberoastable, and one of them is a domain admin, or one of them has admin rights on 50% of the boxes or whatever. So that can be kind of interesting, and that can be very helpful to chart out in a way like this. So we can kind of have a hit list of, okay, you should be remediating these users first because of the level of privilege. So that's one thing that's kind of interesting, but what if we also add another element to this? What if we say, all right, these are my Kerberoastable users, but the Kerberoast attack being successful depends on that user having a weak password that can actually be broken. Okay, well, let's try to break all of them. So here's all of our users that are Kerberoastable that also have a weak password that we were able to crack a password within some reasonable time frame, 24 hours, 48 hours, whatever. So when you're looking for remediation strategy, and you're looking for low-hanging fruit, which is exactly what we're talking about here, this is like zooming in and saying, here is your extreme risk. You need to fix this immediately. There was a customer that we did this for recently, and there was a user that had admin rights on 97% of their systems. His password was changed, let's just say a long time ago. We showed them this chart, and they deleted the user within the hour. And a huge amount of attack surface was removed basically instantaneously. So a pretty big win. What about this? So when we're looking at strategies to figure out how can we reduce attack surface in AD, it's useful to have very basic statistics that will apply to any domain. And so we hone in on this. We hone in on what percentage of users in Active Directory can compromise a domain admin. This is a very simple concept that we can actually empirically measure thanks to this tool. What do I want to say? I want to say that it is very common that this number is 100% in Active Directory. So let's go back to our overall resilience methodology, and now we want to look at how we can generate and validate these, so to say, remediation hypotheses. And our objective here is to eliminate or mitigate as many attack paths as possible using practical and measurably effective strategies before we actually attempt to deploy them in production. So when we say practical, we mean we don't want to go in someplace, or you don't want to do this yourself and then come back and say, well, you just have to re-architect the entire forest. It's easy, and everything will be fixed, and everything will be solved.
Go implement our forest tomorrow.
Yeah, we'll do it tomorrow. It's not practical for most organizations to go through that process. That process can also be extremely expensive, as a lot of people know. So what we're looking for are the, so to say, surgical and precise changes that we can deploy within days or weeks and not years. So here's an example of what you might see in Bloodhound. This is a user over here on the left called ERmore0011. And what we're looking at here are all of the shortest attack paths to domain admin. And that word shortest is absolutely vital. So in graph theory, it is very easy to find the shortest attack path, or shortest path, from any vertex to any other vertex. There are several different algorithms that can solve that problem instantaneously, effectively. Like, think about Google Maps. How long does it take to calculate a route from Los Angeles to New York? Less than a second. It's very, very fast. Google Maps does that because they use a graph to track all that data. So something that we want to help you with is avoid a very common pitfall that we fell into ourselves, and that we also see a lot of other people falling into when they start trying to apply this data in a defensive way. And that pitfall is looking at this information right here and believing or thinking that this is the entire attack path possibility from one user to the domain admins group. It is not. We are looking at the shortest attack paths. So here's a longer attack path that goes through one other group membership step that we couldn't enumerate because it was not part of the shortest attack paths. Here's another attack path that was not enumerated at first because it is also not among the shortest attack paths. Let's look at this a different way. A very common question we get is, how can I see all attack paths? Okay, this is a good question, and it is a question that we asked ourselves when we started trying to accomplish more defensive-centric things using this data. So we're going to look at all attack paths that are possible from this user. This is one user. And this one we're looking at, this is length 0. So length 0 of an attack path. Here's 1. Here's 2. Here's 3. Here's 4. Here's 5. Here's 6. 7. 8. 9. Can anybody derive any kind of insight from that? I can't. That's for one user, outbound attack paths that are possible of length 9. This also took approximately 3 minutes for the database to return the results of this query. Why is this? This is because finding all paths means you have to include the longest path. Finding the longest path in a graph is a very well-studied problem in graph theory, and it is understood and known to be non-polynomial hard. It is an NP hard problem. This is true for directed cyclic graphs, which is what the Bloodhound attack graph is. If it were an acyclic graph, then you could solve this problem in linear time, which also will be a very, very, very long time. So, shortest attack paths we look at in customer environments, and this is how many attack paths we found in one of those networks. This network had 8,000 computers. All of the possible shortest attack paths from any user to domain admins, the domain root, the domain controller, whatever. 20,346,385. I don't know about you, but I don't want to go through each one of those.
It's like an average Tuesday. I mean,
we have 15 minutes left though, so we're gonna start with number one. Okay, shortest attack path number one. Stupid joke. So the bottom line that I want to try to drive into your mind is that Active Directory is not a maze. As a red teamer, as a pen tester, you start off with access onto one system, some kind of like beachhead system, and you find your way through Active Directory until you finally get to your objective, domain admin or whatever. Don't think of Active Directory as a maze. Active Directory is a map. It is an extremely complicated it's an extremely complicated map that doesn't follow the rules of two-dimensional geography. So consider this. If we're going from Washington, D.C. to New York, this is the shortest path. Here's another path. Here's another path. Here's another path. Here's another path. Another path. Another one. So don't think about trying to look at all the attack paths. You can't. I'm sorry to say. So what if instead of looking at all the attack paths, what if we change our thinking from, trying to find like a sparsest cut edge into a strategy of isolation? What if we're trying to isolate New York and Washington, D.C. from the rest of the country? Well, we would zoom in on that city and we would understand what are the first and second degree connections that get us there. All right? Let's replace that with domain admins and domain users. So forget about analyzing all paths. Focus on isolating sensitive principals and focus on understanding what the outbound privileges are that are held by the built-in security groups. Also, privileges that are held by more or less all-inclusive security groups in Active Directory as well that are not default and built-in. So how can we do this for domain admins? Well, let's look at how domain admins are exposed. There are several different ways that we can understand a domain admin exposure or exposure for the group itself. So we have credentials in memory, we have abusable ACEs, we have GPO abuse, Kerberoast, AS rep roasting. There's 1,000 ways to skin that cat. Let's focus on GPO abuse first. So with GPOs, if I control a GPO that is linked to an object that descends down and affects a domain admin, if I control that GPO, I control that domain admin. I can do anything I want with GPO. The possibilities are absolutely endless. So in our data, we can look at any user who belongs to the domain admins group. What are the GPOs that apply to any of those users, regardless of where they exist in the OU tree? Also, 9 times out of 10, we see that domain admins don't actually belong to the same OU. So whatever GPOs apply to a domain admin is basically anybody's guess. So what we want to look at is, show me who has control of any GPO that applies to a domain admin where that user is not a domain admin. And I don't really care if a DA can pop onto the DA. I kind of trust them to protect themselves. So we're going to run that query, and it looks like this. So there's a domain object there in teal, and then the GPOs that are linked to the domain head. Then we have 4 different security groups that have control of different GPOs that apply to those DAs. Those users are not domain admins. So what if we remove those permissions, or what if we change the owners of those GPOs from some random group back to the domain admins group? You would think that this would cause some remediation, like maybe this will reduce the percentage of users that have an attack path, or maybe it'll reduce the overall number of attack paths. Or what if we're not talking about GPO? What if we're talking about deploying pause and making domain admins log onto pause? Or what if we're talking about ACLs can be abused? When we started doing this, we thought, I am so brilliant. You are not going to believe this. I'm gonna make it so that domain admins only log on to domain controllers, and we're going to see a huge reduction in the attack paths in AD. So we simulate that change in our graph. Let's say we remove those permissions and change the object owners and the GPOs. So before, it was 100% of users had a path to DA. We change the data set, we simulate that change before we actually put it into production. And after, anybody want to take a guess what the stat is after? Just how effective my brilliant strategy is going to be? 100%. Made absolutely no difference. Why is this? Because the graph is extremely highly connected, and there are other attack paths that we weren't seeing because we weren't looking at all paths, because you can't. What about abusable ACEs? What if we also say, okay, well, I'm still going to trim those permissions in the GPOs because I want to have this strategy of isolation for my domain admins, but I still have all these other attack paths now that rely on abusing ACEs on the domain admin users or the domain admins group itself. So here's an example. We have our domain admins group. We have those users that belong to the group. Inbound object control, if you look at the very bottom there, you can see that there are 3 principals that have explicit control of the domain admins group. But if you unroll that out, there are actually 47 different identities that have control of the group or a user in the group. And here they are. So we can unroll this out and visualize what groups can control a domain admin or control the group itself. So let's get rid of that. Let's focus on that strategy of isolation. Okay? So we've simulated changing GPO control for GPOs that apply to domain admins or computers that are used by domain admins. And we've trimmed permissions inbound on the domain admin users and on the domain admins group. So before, we had 100% of users with an attack path domain admin. After, it's 82%. We're actually making some forward progress. These numbers, by the way, are real. These are real numbers from a real environment. This is what's possible, is once you understand this strategy of isolation, both on the endpoint of the attack path and on the possibilities for where the attack path can begin vis-a-vis local admin rights on domain users, or Kerberostable users, or domain users that have RDP access on systems that are escalatable, or there's a local privacy on those systems. You can whittle this down so that your attack surface is reduced all the way down to 1% or less than 1% of the users in the directory being able to take control of a domain admin. Sometimes we can't get this number this low. I think the worst that we've done so far is being able to take it down to about 6%, which is still pretty good. Once you have those attack paths whittled down and you say, well, we can't get it any lower because there is some business need for a domain trust or for some kind of configuration, instead of having to deploy some kind of non-scalable security control so that you're kind of like surveying every single computer in the environment because you have no idea where the attacker is going to go, you're kind of funneling the attacker so that they have to go through this one system. They have to go through this one user. And those controls that cannot scale, if it's 5 computers that I have to deploy the Windows firewall on and configure inbound whitelisting rules, I could do that in an afternoon. If I had to do that for 100,000 computers joined to AD, it's not going to happen. Everything in this talk is free and open source. The tools we talked about, Bloodhound, the Bloodhound Analytics tool, PowerView, PowerMad, Invoke DC Sync, and the methodology itself is also free and open source. If you look at the Bloodhound Analytics URL there, you will be able to create these charts yourself. And then if you look at this blog post in the top right, you'll see even more detail about understanding the difference between all paths, shortest paths, and all that kind of good stuff. Thank you very much for your time. I think we have about 6 minutes left if we want to take questions here. And then otherwise, we're going to be out in the breakout room to the right over here.
Thank you, guys.
Thank you.